So we will look how the robots are inspired by all these different ways of animal representation of knowledge, and we will zoom in how you can do that representation for robots. So robots work with many representations of their environment, because the nice thing of robots is that there is artificial intelligence that's embodied in the middle of the world. So it needs to have a lot of knowledge about that world. Part is spatial models about a map of that environment. Part of it is models of objects that it can see but also can handle. For instance, if you have a 3D, full 3D model of a cup, then you still need to have a model where to grasp that mug. So you see already that object model is directly coupled with perceptual knowledge from how to grab such a cup. So first you have to know that you have to advance to that cup, and then if you're close by, how to close your hand, your gripper, to grasp that part. So that object model and the perceptual model can be really tightly coupled. What's also important, that the information that you need in your behavioral models, how to acquire that. So that means that if you have such a cup, I have a cup with me, yes. That you, if you want to see from this side, you don't see the handle, but you know if you have to turn it, that you can actually see the handle, and that you know how to grab it. Okay, to do that, you also have to know how long your arms are, what typically, what your speed of your arm is, etc., etc. So that you also have to have a good model of yourself, and you need a top level model, what you want to acquire, what your tasks are, and how to survive on the long run. Okay. So that's the type of information that you wanted to know about. Then the question is, how do you store it? On the most detailed level, it's a quantitative where you all have all measurements collected. On a certain moment, you can process that, and you have qualitative information. That's, for instance, if an object is there or not. Part of that things are persistence that you have to remember on the long run. Part of it, the cup you can get once you're ready with drinking, and you can also have that on a symbolic or a sub-symbolic level. What you see for the robots is that you can store that on 3 different levels. On the lowest level, you have the reactive layer, where all the sensory information is processed and directly coupled to actions. So that's information you can directly forget. Some of that information you aggregate to build a dynamic sensory map of your local environment. That's great if you want to avoid obstacles, for instance. And part of that short-term memory you're going to store for next experience, that if you have to travel the same route the next day, that you don't have to start completely from scratch, and then you can store that sort of information about, for instance, your maze in a prior model. So you see on one hand that you have from instantaneous information to the long-term memory, and you see also a coupling to the different behaviors, and you see also how that's coupled to from transitory knowledge to persistent knowledge. So we will look how that different layers are coupled to behaviors, and how you can have examples of that transient behavior in behavioral maps, how you can create sensor-based cognitive maps, and how you can incorporate previous experience with a priori representations. So, one example is the behavioral encoding of your perceptual process, your short-term memory, and your response that is in your motor schema. And you can have there different representation of map types in that short-time memory. So here you see that there is a grid put over that short-term memory, but you can also have feature maps and topological maps to be stored in that short-term memory. So what are those grid maps for robots? What you can do that with a sonar, you can have a certain measurement that there is an obstacle in front of you, and if you each of those measurements that gives a Gaussian distribution where the highest chance of an obstacle is there. So you know that 3 or 4 meters in front of you there is an obstacle, but it can be a little bit to the left and a little bit to the right. And that observation you can use as a sort of stamping to create a map of your environment. And you see that on the right side of the presentation, that you can see what is free space and what where you can expect obstacles. And if you're then driving around and you keep on stamping, then you can make a sort of grid map of your room, and you can base your navigation behavior on that. And you can see how how sort of grid maps are based with the Minerva robot. So the link of the video that I can provide later on. Okay. So what are examples of this sort of short-term memory in different behaviors? One of them is that you want to do exploration, and that you don't want to be on the same place again, and that can be stored but by putting a sort of memory where you have been, what path you have already driven. You can put a little bit of order there, and it means that you never travel the same path again, so that you store your path in a short-term path memory. Another short-term memory is that you build up a sonar map of your environment, and sorry. And your continue to build up your sensor measurements to a line, and that line is the wall that you are going to follow. And you only have to do that for the wall that's nearby. You don't have to make a complete map, but you want to combine several of those sensor measurements to one concept of a wall. Another thing that it's great is in obstacle handling, where you can see the different obstacles and make a sort of force field away from those obstacles, and that's also an example of a short-term representation of your local environment. And that's not only with it true for subsumption architectures. You can also do that schema-based, and there with it you have an own sort of percept, so an own sort of short-term memory for each of the concepts that are important for your different behaviors to display. And that can be with it quite complex. That can be a sort of segmentation, like with it each of the segments, how they with it look like the eyes of an insect. But you can also make histograms of directions you like to go or that you don't want to go. Why do you need a little bit of that long-term, short-term memory? So not only one observation, but two observations. Because in principle, if you have one observation, you have only a vague idea of an obstacle. But if you move your robot and you have two observations, and with triangulation, you can get a much better estimation from both the range and the angle of the obstacles. So in that way, with combining a few observations, you can make a much better measurement of your environment. So what's often done is that all those different observations are combined into features, and that are features that you can recognize because they have a certain fingerprint, and that means that you can recognize one wall as white, other one as the ground as brown, etc. So you know that for a short term, if you see that wall again, that you see the same wall, because each of those features has a small fingerprint, a feature that you can store in a short-term memory. That's not only can be done with sonars, but also with lasers. The nice thing of laser maps is that they are far more accurate than sonars. So you know your location of your wall with an accuracy of less than a centimeter. So you can have far more detailed features, but also you can look much farther, up to 80 meters. So still you have to aggregate a lot of observations into a local map. And you can do that in 2D, but you can even make with it 3D models of your environment. And then you can combine those models into lines or even 2D with it 3D surfaces. Okay, and that's great, and that you can use that if you want to explore an environment in 3D with a drone, if you can get a laser scanner on top of that drone. So that's a lot of information that you store in metrical, say in a grid where it's all precise measurements. But often you don't want to navigate on a full metric map, but more on a route. That means that you combine all those measurements into a graph, and then you make a topological map. From there's the corridor, there's your crossing, there you can pass through the door. And that's great, because when you do have graphs, you can really do easily search through that and find a shortest route. So examples of this is this on the left side you have a metric map of an office environment, and you can make a topological map for that. And the nice thing is that each of those nodes in the topological map, you can combine it with certain of percepts, if you can recognize or if you're on a T crossing or in a corridor. And you can also combine, if you're in a corridor, that with behaviors, follow that corridor until you come to the next crossing and combine it to reactive behaviors. So that's what you can easily create from a metric map, a topological map. Vice versa is much more difficult. Why do you need such a topological map? Is because they are easily coupled with routes, but on routes you need a lot of information about what you see along the route. So on the topological map you put things where you could start looking for, so attention points. So what I say, if you give a route to a certain city, drive along the highway until you see, for instance, the advertisement of McDonald's. They are always nicely on a crossing, so you know where you have to look for, and you can continue driving until you see that specific landmark, and then make your decisions next. And then you can say, okay, if you have seen that landmark, then you still have to go to parts further, and then take the next crossing. So, what important is that you along the route you have landmarks. Landmarks are really special. First, they have to be really perceptual, very distinctive. So you shouldn't see them too often. You want that they are recognizable from very different scales, so you have to recognize them from nearby, but also from a large distance. And in principle, you want to see them that they look the same from all orientations, so that if you come from other direction, that they look the same. So in that sense, the Eiffel Tower is the ideal landmark, because you can see it from the whole city of Paris. You can always recognize it. There's only one of them, and from every side it looks more or less the same. The other thing, what's important for landmarks, that they should be located on points where you have to make decisions on your route. So if you pass Paris, if you go to the west coast or the Mediterranean, that's a place because all highways come together in Paris, and from there you have to make certain decisions. So it also have to be placed on points where you have to make decisions on your route. So how do you make the transition from a metric map, floor plan, to a topological map? Is you can easily make a skeleton from that map with all the routes that you have. You can make different decision points, and on that, if you can add on each of the decision points a good landmark, then you can make a drivable path for a behavior-based robot. So the first ones were the ones where only the observations were coupled to the nodes. So you indicate on each node which landmark to look for. But if you then travel from the top to the middle to the right, then you see that because you're never sure what sort of behavior you execute, that you get more and more unsure where you are. And if you are too far away from the last landmark 4, then you cannot recognize it anymore. Later on, they made nodes where the traveling from one landmark to the other one is coupled to a typical behavior. Stay in the middle of the corridor, and then you're sure that you don't have that uncertainty where you are, because you always know that you're in the middle of the corridor, and then you only have to drive until you see that final landmark. So the topological graphs work much better if you couple them to behaviors. So what's the main advantage? If you have such a map that's coupled to behaviors, you don't have to concern anything anymore with all the navigational errors anymore. You don't have to build up on a long-term metric information. You only have to recognize, give, say, the features that you have to recognize on the environment. But that's also the downside of it, because finding the features that are easy to recognize, that's not that difficult. But often, if they are that easy, then you can see them everywhere. Examples are lights on the ceiling, or the boards of the different rooms. You need to get the right balance from features that are not too common, but also that not are completely unique. That makes it hard. And for sure, if you live indoors, then a lot of corridors all look the same. And that's why most of the scientists always put posters on their door, so that they could recognize their own room even when they are in deep thought. Okay. The other thing, what is really the trend in robotics, is that you don't not estimate, say, or one location, but you take a numerical approach where you sample all possible positions that are possible on the map, and based on your observations, you get that some locations are more probable than others. So you store not only the location, but also the probability. And then you can make nice maps that's running now from ceiling map from the Smithsonian part. And you see in a certain moment you are starting to recognize the patterns that are in ceiling, and then you know for sure where you are in the Smithsonian. And in that way, with it, you can couple that probabilistic approach with navigations for different robots. And you can also easily exchange that between two robots. So we talked a lot about the environment, but robots are not robots if they can also handle objects. So you need to learn of all the objects that are around you, but you not only have to learn to recognize them, but you also have to learn how to handle them. So that's one example of the HumanBot challenge, where you have two small humanoid robots that have to live in a small kitchen, and you can then give them different sort of vegetables, and there then they have to recognize which vegetable is in the kitchen and what is the right way to grab each of those vegetables. The nice thing what they've found is that for long-term storage, it's nice that each robot learns how a different vegetable looks like, but they also made a sort of Wikipedia for robots, and that's not only what sort of objects there are, but also how to handle them. So, example of it, if you have a recipe to bake pancakes, that you know that you need eggs and milk. Eggs always have the same shape. They only have sometimes a different color. Milk you have to know that it's white, but it's always stored in packages. So you have to know in the different countries how the different packages are looking like. But if you have recognized that the package, then the weight and the grabbing point is often the same, and you can share a lot of this sort of information, how to handle objects, on the Wikipedia of robotics, say RoboEarth. And there we have stored so that this sort of a priori data in the internet. Okay, so that's what I wanted to tell today about representational issues on robotics. So we've seen that a lot is stored about the environment, both the maps and objects. We've seen that all this information is only relevant if it starts to be active. So if it's directly coupled to what you can do with it, with the behaviors. We've seen that you can sometimes do it Euclidean, but often it's based on polar plots and gradients. And we've seen that robots can handle all of that and can easily translate one information to the other, so that it's also available on a higher level to make decisions which behavior to take. Okay, thank you for your attention, and see you next time. And this is the wrap up what you have learned today.